Welcome back to the next video, everybody. Today we're going to be looking at part 2 of proposition 4 en route to proving the general case of R equals T for the proof of Fermat's last theorem. So in this video, we're going to be discussing full Hecke algebras. Let's get into it. So right now we have two notions of Hecke algebras. Let's let L be a prime. We'll let K over QL be a finite extension with ring of integers O and residue field K equals O mod lambda, where lambda is the maximal ideal of O. We'll also fix embeddings K into Q bar L, Q bar into Q bar L, and Q bar into C. So far, we've defined Hecke algebras over O in two different contexts. The first context is as an algebra, let's say T sub O, generated by all the Hecke operators acting on some suitable space of modular forms. And second, as a subring, which we called T sub sigma, of a product of fields generated by coefficients of new forms, which all admit the same mod L representation. So what we want to do is, and what we're going to need to do, is identify the reduced Hecke algebra, as we call them, T sub sigma, as actual localizations of the full Hecke algebras T sub O at certain maximal ideals. And so the goal of this video is going to be to establish some prerequisite knowledge to be able to do that. Okay, so the notation is as follows. We'll let gamma be gamma h of n for some natural number n and some subgroup h in Z mod n Z cross. So see chapter 3 for what I'm talking about here. We're just taking some congruent subgroup of SL2Z, basically. We'll let TZ be the subring of endomorphisms of S2 gamma generated by all the Hecke operators T sub n for all little n, and all the diamond operators bracket D for all D in Z mod n Z cross. If R is a ring, we'll define T sub R to be T sub Z tensored up to R. T sub R acts faithfully on S2 gamma R, so this would be all the cusp forms with R coefficients with respect to gamma. And it's also finitely generated and free as an R module. These are just basic facts. Okay. So here's a lemma we'll need. Lemma T sub R, I'll call it. It says two things. First of all, T sub R is generated as an R algebra by either of the following. Either all of the Hecke operators T sub n, or T sub P for all primes P, and the diamond operators bracket D for all D in Z mod n Z cross. This is a little bit surprising. And then two, let's suppose that big D and n are coprime. If big D is odd or 2 is invertible in R, then T sub R is generated as an R algebra by either of the following. The Hecke operators T sub n for all n coprime to big D, or the Hecke operators T sub P for all primes P not dividing D, and then all of the diamond operators bracket D. This is a pretty standard fact. I guess for a proof of the first part, you can see diamond im. And for the second part, you can actually see Weil's original paper, page 491, although I'm sure this is proven elsewhere as well. Okay. Now, if we look at T sub K and T sub little k, these guys only have finitely many prime ideals, and they're all maximal. So by the going up and going down theorems from commutative algebra, since T sub O is finitely generated and free as an O module, its maximal, respectively minimal prime ideals are those that lie over lambda, respectively the 0 ideal in O. And so the natural maps T injecting into T sub big K and T sub O surjecting onto T sub little k actually induce bijections as follows. There's a bijection from the maximal ideals of T sub big K with the minimal ideals of T sub O, and the maximal ideals of T sub little k with the maximal ideals of T sub O. Now, O is complete. So the natural map T sub O to the product over M of T sub M is an isomorphism, where the product is over the finite set of maximal ideals M of T sub O, and T sub M denotes the localization of T at M. Moreover, each T sub M is actually a complete local O algebra, which is finitely generated as an O module, and each minimal prime script P of T sub O is contained in a unique such M. And so we're going to look at an enlightening diagram now. We'll let S2 gamma K bar NN mod GK denote the set of normalized eigenforms in S2 gamma K bar modulo GK conjugacy. And we'll define S2 gamma little K bar NN mod G little k similarly. Then, and you can see DDT page 108 for more details, we have the following commutative diagram of finite sets. So S2 gamma big K bar NN mod GK is in bijection with the max spec of T sub little k, so the maximal prime ideals of T sub big K. And that is in bijection with min spec of T sub O. So this is the set of all minimal prime ideals of T sub O. The top guy surjects onto S2 gamma little k bar nn mod g little k by the Deligne-Serre-Lifting lemma. Here's a reference for that down here. That guy is in bijection with max spec of t little k, which is in bijection with max spec of TO. And then min spec TO surjects onto max spec TO. So most of this we just got done talking about, but you do need the Deligne-Serre-Lifting lemma for this top guy. Okay. Now, a little more on this diagram. If you let M be a maximal ideal of T sub O, then the maximal ideals of T sub big K mapping to M are exactly those prime ideals P, such that P intersect T sub O is in M. And in addition to that, the natural map from T localized at M tensored up to K to the product over these primes P of T localized at P is actually an isomorphism, right? Where the product, just to be clear, is over these primes P that we just got done talking about. Finally, the above diagram on the last slide is well behaved when K is replaced by a finite extension K prime. I'll either let you think about what that means, or I'll send you to DDT page 109 for the details. Okay. So let's revisit Galois representations now. Let P be a maximal ideal of T sub big K, and let M be its associated maximal ideal of T sub O as per the above. Recall from chapter 3 of this playlist, or also see DDT page lemma 139, that T sub L, Tate module, JHNs, the Jacobian that we're working with, tensored up to K over Z sub L is free of rank 2 over T sub big K. So reduction mod frac P yields a Galois representation, which we'll call rho sub frac P from GQ to GL2 of T sub big K mod frac P, which is unramified at all primes P, not dividing NL, such that for these P, the characteristic polynomial of the representation evaluated at frob sub P is x squared minus TPX plus P times diamond of D modulo frac P. Also, rho sub frac P is defined over T sub O mod M, and we write rho sub M for its semi-simplification from GQ to GL2 of DO mod M. And this is unramified outside NL with the same characteristic polynomial for frob P as before, except for mod M instead of mod frac P. Okay, all standard stuff, just background. Now, if G is a new form for the GK conjugacy class of eigenforms in S2 gamma corresponding to frac P, again, as per the above slides, then T sub big K mod frac P is isomorphic to the field K prime G, which is like the local number field of G. It's like the L-adic, it's not the number field of G, the number field generated by the coefficients of G. It's the finite extension of QL generated by those coefficients. And furthermore, rho sub frac P is actually isomorphic to rho sub F. And so these representations that we developed in this talk, they're actually isomorphic to familiar representations that we've been dealing with since chapter 1 of this playlist. Moreover, rho bar G is obtained by rho sub M, but actually just by extension of scalars. Okay. Now we're going to try to describe T sub K a little bit better. So suppose K contains the coefficients of all eigenforms of level dividing the n that we were given. We'll let cal n sub gamma denote the set of new forms in S2 gamma. And we'll recall from the basic theory of modular forms, you can see, for example, DDT theorem 1.22, although this is kind of in a variety of places, that S2 gamma K, so the cusp forms with respect to gamma with K coefficients, this is just actually the direct sum over F in n sub gamma of what we'll call SKF, which is the space spanned by the linearly independent elements in the following set, the set of all F of A tau, where A divides n over n sub F. Okay, n sub F is the level of F here. Okay, well, let's let F be, let's give F kind of a standard Q expansion with coefficients A sub n of F, and we'll let F be in n sub gamma, and we'll make some definitions. We'll let TKF be the image of TK in the K endomorphisms of SKF. We'll let AKF be the polynomial ring over K in the variables we'll call UFP indexed by the prime divisors of n over NF. And we'll let IKF be the ideal in AKF generated by the following polynomials P sub FP of UFP, which are given by the following expression. U of FP, so our variable, to the VP n over NF minus 1. So this is p-adic valuation here, times U squared FP minus APF UFP plus psi F, the character of F, evaluated at P times P. And this is for primes P dividing n over NF. And if P does divide NF, just set psi sub F of P to be 0 as per usual convention. It's not hard, and this is done in DDT on page 111, for example, to show the following. We'll call this lemma TK, and we will not prove this because it's not hard, like I just said. There is actually an isomorphism of K algebras between TK and the product over F in N sub gamma of AKF mod that ideal IKF we just got done describing. And so in particular, TK is actually a complete intersection ring over K, thanks to this isomorphism. I think that's a great place to stop. We'll look at part 3 of the proof of proposition 4 from last video starting next video. Thanks for watching, and I'll see you then.